Hey, good morning, everybody. Thank you, Corey. Thank you, Dale. Well, thank you, Brandon. All right. I was talking about those complex functions as mappings, which is a fascinating subject by itself. So, we examined several of those uh, maps, including linear, including reciprocal function. And finally, on last Wednesday, I talked about linear fractional transformations, all right? Now, um, just uh, and I gave you some examples and how beautiful this function is. This is one of the major functions that we need to know. Uh, okay. Okay. So linear fractional transformation, although the general uh, format is you have a constant here, but the main thing is this one, that this function, as we discussed earlier on Wednesday, maps the whole upper half plane into this disk, okay, unit disk, in such a way that this I here, right here, I goes to zero, right? If you plug I here, you get zero in UV plane. And the combination of this one and some other uh, mappings that we earlier have discussed now gives us a bunch of good examples. For example, here's the general format, of course, e to the I alpha. Uh, Alpha can be anything, but what this does is just rotates, okay, rotates the whole disk a little bit. Um, anyways, here is an example. I think I discussed this one with you last time, but it helps. Um, 17.1, I haven't started 17.1 Dell yet. So this is, oh yeah, oh, this is 17. I thought you are, sure. Just let me finish this lecture and then tell me example what the problem you're looking at. Um, so here is um, a set. This is how the problems in this chapter look. They will give you a set, a portion of XY plane, right? And they will tell you, for example, well, go ahead and find a function that maps this into something else. In this case, the unit disk. Well, of course, you need to uh, graph this thing. This is the set of all xy's. There is no restriction on y, but x has to be less than or equal to -1. So here is the shaded area. This is S. Now, in order to map this one onto unit circle, of course, we think of this thing. right? This is the map that sends upper half plane into unit disk. So somehow we need to uh, make the problem ready for that one. So here is what we did last time. So we will rotate the whole thing 90 degree to uh, uh, the sort of uh, clockwise, okay, which is a negative direction. And 90-degree means multiplication by uh, e to the negative pi over to I, which is negative I. So multiplication by negative I converts this half plane into this one. Then you bring one unit down, which is this, all right? And now you apply that transformation that we know maps upper half plane into the unit disk. So, and here is the last motion or transformation. And if you put all these together, here you are multiplying by negative I. Then you are subtracting I. And then you're applying this, putting all together, this is the transformation. Okay, after simplifying, this transformation actually does the job, maps S into this unit disk. Okay, so as I said, um, the problem that we are going to solve um, could be combination of these maps. You need to apply several of these maps and in several steps. Okay, here is another one that also I discussed last time. I'm not going to repeat it. Uh, Here is another one that tells you how creative you gotta be. So this time, this is the set. Oh, look, it says the set of all xy's. X is bigger than 1. Here is x bigger than 1 in this area. And y is less than negative 1. Here is negative 1. So this is S. And we want to sort of map this into that unit disk. Okay. Well, you gotta, when it comes to mapping into unit disk, we understand that we need to use that linear fractional transformation. But we need to prepare for that one. All right. We need to prepare for that one. Eventually, we are going to use this, but we need to prepare it. And prepare, that preparement here means we need to have an upper half plane. So this is what I'm going to do. First, bring the whole thing by a transformation to this point. Okay. So you, in order to bring it up 1 unit, and so you subtract 1, right? Actually, we got to add 1. And so we need to add 1. The coordinate of this point is 1 minus I, right? we want to bring it here. So okay, here is negative I. To bring it up, you add I. Here is 1. To bring it here, you subtract 1 from x, the real part. So that's it. So after this translation, you converted that s into the fourth quadrant. Now we better bring it into the first quadrant. And bring it in the first quadrant means rotating it or 90 degrees, right? So the next move is rotate 90 degrees. If I rotate this 90 degrees, this will be the result. But we don't need a quarter. We need a half plane. So if I square it, remember squaring. If I square it, it becomes the whole upper half plane. Okay. After the squaring that we have now, upper half plane, now we are ready to apply that linear fractional transformation. Now we apply this and we get into this. All right. So why does squaring? Okay, squaring the squaring sort of okay, let me explain why squaring does that. So when z is r e to the I theta, and you square it, you get z squared, right? R squared, fine, but e to the 2I theta. What does this mean? This means that if you have a ray like this, then the angle here is alpha. When you square it, this ray becomes another ray. The points on this ray will stay, the modulus will change, of course, but the angle will become 2 alpha. So after squaring, what I have is 2 alpha, right? This is 2 alpha. This is, as I said, some very simple observation will help you. Squaring makes this ray, converts this ray to this ray. So this 45 degree, this one, 45 degree, becomes, when you square it, it becomes pi over 2, becomes this one. And so forth, right? This pi over 3 is 60 degree. When you square it, becomes 120 degree. So it becomes here. Eventually, this ray, the y-axis, when theta is 90 degree or pi over 2, when you square it, it becomes twice, which is pi. So that is why just looking at the rays will help you to realize that why, when you square this part, you will get the whole half plane. All right. Is this clear now? Yeah. Okay, good. Um, so this is what I meant by we need to be good at all these functions that we already um, studied. So we studied z squared, so we should sort of have in mind that squaring the first quadrant gives us the upper half plane. All right. Now, and of course, you put these actions together. All right. Remember, the first action was translation to this point. Then the second action was multiplication by I. So you multiply this by I, then you square it. So here is what happens. Then you apply this function. So the function that maps S onto unit disk is this one. Okay, is this one. Now, of course, you can go ahead and if you want, multiply it out and take care of simplify it. But as far as I'm concerned, if in your test you just produce this one, that's perfectly fine. Okay? Any comment, any question? Well, the next function that I am going to discuss is sine z. It's another very interesting function. When you look at these calculus, the graph of sine x is pretty simple, right? It's just this one alternating going up and down, all right, always between -1 and 1. This is in calculus. Y equals sine x, when x is a real number. But when it comes to complex, again, we need to remember that those properties of sine z. Sine z is certainly periodic function. And that comes from the fact that e to the 2 pi I is 1. So being periodic function, and the period is 2 pi, okay, period is 2 pi. So it is enough to study the function in one of its full periods. And the periods, the imaginary part of z has to be between -pi and pi. That's a horizontal strip. Okay. Then instead of z, yeah, z between -pi and it is better, I say, imaginary part of yeah, or this is the real part of x, real part of z. Okay, good. So the other observation about sine z is that we know we developed this formula. The modulus of sine z is when z is x plus iy. And although sine of x is between -1 and 1, in this case you're squaring it, it's between 0 and 1, but this guy is unbounded. Sinh square of y, and y can be, x can be between -pi and pi, but y can be anything. So sine z is unbounded. And when we were studying sine z by itself, I sort of told you that in calculus, when we say sine x equal 10, we say, oh, that's ridiculous. But in complex, actually, sine z can be 10 or any number. And we solved the equation like this when we were talking about sine z. Okay, Brandon has a question here. Let's see. It's talking about previous. So see what happens. The first move is this one. The second move, we want to rotate this, right? Combination of rotation and this move. So you're actually now, if you want to go from here to this one, to rotation, from here to here, first you translate, then you multiply by I. So it will be I times the whole thing. Okay, I times the whole thing. So it will be I z negative I and I squared, and I squared is -1. So that is it. Okay, so after bringing this, you want to square the whole thing. Squaring the whole thing means squaring this. And then you want to apply this thing. So that's it. Okay, good. I'm glad that you're paying attention to these little details. All right. The okay. So science is unbounded, certainly. And it is going to be 0 here if these two are 0, which means x is 0, and sinh y, and that's when y is 0. So x has to be k pi. Well, these are some little observations that will help us to figure out how sine z behaves as a mapping. Now, here's an identity, a trig identity. It's easy to verify, all right? Sine of pi minus c is sinus. But in what does this do? Okay, here is the sort of analysis of this very innocent looking identity when it comes to mapping. Look, I told you it's enough to check the behavior of sine z when x is between negative pi and pi. But look at these two strips. When you choose a point z here, negative z means the, this one. Here is negative z. So if this is the coordinate here is x, y, the coordinate here is negative x, negative y. So negative z is, in effect, the reflection with respect to origin. If you choose z in this shaded area, here is pi over 2 pi. Negative z is here. And if you add pi, it comes here. All right? Or if you choose z here, negative z is there, and adding pi bring it here. Which means this pi minus z, what it does, it maps this shaded area to this strip, okay? And when you apply sine, the sine of z and pi minus z is the same. So, as I said, this innocent-looking identity, its geometric interpretation is, if I know the values of sine z between 0 and pi over 2, based on that, I know the values between pi over 2 and pi as well. So, the conclusion, when it comes in between these two parts, I better just ignore this shaded area. I better just concentrate on 0 pi over 2 times r. This is that vertical strip, 0 pi over 2. All right? So that's a very good observation. Do we have any other observation concerning sine z? We certainly do. Another innocent identity is this one. Sine of negative pi, negative z is the same as sine of z. Well, the geometric interpretation of this identity is here. Now look at this shaded area. What is negative pi, negative z? Negative pi, negative z. If you choose z here, negative z is right here. And if you subtract pi, it becomes in this area. And we know that sine of these two are the same based on this trig identity. What is the conclusion? The conclusion is, if we know the behavior of sine z in this strip, we know how it behaves also in this strip based on that identity. So I don't need to consider this shaded area. All right? Now, putting these two together, that means it is enough to consider to study sine z as a mapping, then x is between negative pi over 2 and pi over 2. Because as if we know the behavior of sine z in this strip, definitely we know what happens here and what happens in this strip, okay? So this couple of observations, but beautiful observations, all right? It will tell us that, you know what, when it comes to sine z, just go ahead and concentrate on this one. Then x is between negative pi over 2 and pi over 2. Just concentrate on this one. Y can be anything, all right? That vertical strip, all right. But I'm going to simply look at half of it instead of all of it. Look at this half. And this half, by this half, this is, I mean, the upper part of that vertical strip. It's interesting when you apply sine z to this part, you will get upper half plane. Oh, this is extremely important now, because we like upper half plane, don't we? After having upper half plane, we apply that linear fractional transformation, and we will map upper half plane into unit disk. So this becomes extremely crucial then. And the idea that why this half strip goes to upper half plane is pretty obvious. You just look at the boundaries. Look at this line. The sign of that, you know, y, when y goes to infinity, that sign of z is unbounded, right? Sign of z is unbounded. So the image of a in this is here. Going down, sine of pi over negative pi over 2. All because of this identity, all right? Sine of pi over negative pi over 2. Now, at this point, y is 0, so this is 0. And here you get b prime, because sine of pi, negative pi over 2 is negative 1. Negative 1. So this is mapped to b prime. When it comes to zeros, what is sine of 0? It is 0. So you move along this line, then go up here, so you're actually going right there. Now, move to the c. Sine of pi over 2 is 1. Well, okay, c prime. And of course, when you go along this line, we know that sine of pi over 2 is 1, but this part is going toward infinity, so that's it. Okay, so this boundary goes to x-axis. How do we know it is not lower part? It is upper part. Well, you can just use, for example, I, the image of I will be somewhere there. So here are the analysis, all right? Then x is plus minus pi over 2, which is along this line and this line. This is what we get, okay? Conclusion. This half half a strip, the width is pi, right? Remember this, the width is pi. If you apply sine z, you get upper half plane. But what if we have another type of half a strip, which is parallel to x-axis or y-axis? Can that be mapped into upper half plane? Of course it can, right? Of course it can. Here's an example. Here's an example. Let's look at the set of all points in the plane. Y is non-negative, but x is between -3 and -1. Now you need to graph this and get a good feeling of what needs to be done. And then I want to map it onto a unit disk. Okay, here is S. Here is S. All the x's are between -3 and -1. But we better have it in the exactly middle, right? So if you add 2, you're shifting it to the right 2 units. So the first move is shifting to the right. If I shift it to the right 2 units, this is what I get. Is this good enough? No, because I better have -π/2 and π/2. And that is when you multiply by π/2. Multiplication by π/2 gives you this. And now you apply sine z. If you apply sine z, you get upper half plane. And after having upper half plane, of course, we know that this will take upper half plane into this unit disk, okay? So you see what I'm doing right here. Combination of several moves. And those moves are, some of them are very basic. When it comes to more complicated one, it's a sine z. You need to memorize, to remember that sine z takes this part to upper half plane. And you also need to completely understand that this function takes upper half plane to the unit disk. So we can of course combine these different steps, but there is so the first one, you move 2 units plus 2, then multiply by π/2 here, then apply sine z. Okay, so this is what happens. The first multiplication, adding 2, then multiplication π/2, then sine z, and after sine z, then this linear fractional transformation. Okay, any question about this example? Image is a little blur. Let's see if I can make the image sharper. Yeah, better. Any comment, any question? So today I sort of covered this important function sine z. Okay. Now I do have some times left, and let's see. We had a question from Dale. Could you please tell me exactly which problem of 17.1, Dale, you want? And oh, number 16. Let me get the textbook. All right, 17.1, number 16. Okay, so here is number 16 from based on my textbook that I don't know if it's the same thing that you got. You know, 17.1, number 16. It says, a sketch or a graph given region and its image under the given mapping. Number 16 is sort of, this is what we want to do. Apply z equal 1 over w equal 1 over z. Okay. So we need to apply the function. Different wordings, but that's the same thing, right? W equal 1 over z. And find the image of this set. It is a combination of, there are two conditions here. First of all, it says z is less than 1/2. The second condition says the image of z is positive, imaginary part, all right? And imaginary part of z is positive. Good. Good question. Well, it is reciprocal function. We want to apply reciprocal function. Remember, reciprocal function is combination of inversion with respect to unit circle and conjugation. All right. So before doing this problem completely, you always need to, of course, know the basics. You need to know that 1 over z is combination of inversion. I'm not saying or writing with respect to unit circle, but it's inversion and conjugation. Okay, good. Let's have a little picture here. Here is the circle 1/2. But imaginary part is supposed to be paused. This is it. And here is good. The inversion of 1/2 goes to circle of radius 2. Okay? So here's the inversion. Well, better have it lower because I want the circle of radius 2. So this is a circle of radius 2. Just the inversion does this, okay? Not conjugation. So the whole thing here, the inversion brings it here. This is, maybe I should sort of add inversion. And conjugation. Next, conjugation. Conjugation of this with respect to, conjugation is reflection with respect to x-axis. UV. This is it. Inversion brings it here. Conjugation brings it here. So the image of this under 1 over z is this one. Okay? Does it make sense, Del? Uh, yeah, exactly. Conjugation is just flipping it over. That's what conjugation means, right? When you have, let's say here, when you have x plus iy, the conjugation is x minus iy. Just here is x minus iy, all right? So reflection x minus iy. So stays the same, but and the imaginary part, the sign changes, comes down. Yes, exactly. Always. Always for 1 over z, you follow these two motion, uh, this inversion with respect to unit circle and then conjugation. Sure. Any other comment or question? As I said, this is this it's a fascinating subject, mapping, when you think about uh, complex functions as mapping. And we do have a good application when I talk in chapter uh, 18, uh, and we want to solve a Dirichlet problem. And the Dirichlet problem is being solved on unit disk, right? But sometimes they are asking you to solve it in somewhere else, another uh, region. So we need to convert that region to the unit disk when where the problem is already been solved. And after finding the solution, get it back to that previous region. So that is why the mapping becomes extremely important. Well, Dell is asking another number 15. Here, let's see. Yeah, that's a good one also. Same thing, because you're dealing with a circle, which is inside the unit disk. So uh, number 15 is so here is 17.1, number 15. So the area that we want to work with is, so we want to apply the reciprocal function to this one. It's a circle. I mean, it's a disk, of course. That's, I guess, yeah, that's it. So let's look at this one, and with respect to unit um, circle, uh, here is the unit circle. Well, it has to come a little bit down. Sorry about this. I do these circles better on the board. And here is this circle. This is unit circle, centered at 1/2, radius 1/2. So it's this one. Okay. Well, the image of this point is itself. So I'm talking about the inversion. When you apply 1 over z, this part goes to in UV plane. I have done this, I guess, in while I was teaching it, goes to this vertical line. And here's one. So this circle goes to this line. Okay? And any point here, if you want to use the inversion, so uh, we could do it also analytically by, um, but this is fine. This is UV plane. Okay. And the question now becomes, what about the points in this disk? Is it going to be in this side or on that side? The answer is it's going to be on that side because this point 1/2, this is 1/2. If you plug it in here, apply 1/2, you get 2. So 1/2 goes 2. So here is the image of that disk under 1 over z. Okay? It is yeah, 1 over z, we proved that it takes the totality of lines and circles to lines and circles, okay? So if you have a line, the image can still be a line or can be a circle. Point 1 is pretty obvious. Here is 1, right? So plug 1. Let's see if 1. What do we get? Of course you get this one, right? So, because if you plug 1, you get 1. Okay. Well, I'm glad I had some time left so that I could answer these questions. You can ask more questions on Thursday, but I believe you have a test on next Thursday. So study hard. Um, so now in this problem doesn't say imaginary part of z is positive. In number 15, it doesn't say that. If it says, sure. If it says, it does. Yeah, in number 16, it does say imaginary part positive, but in number 15 doesn't. But if it says, sure, the imaginary part positive means half of this and goes to half of this, all right? Now, which half? Then it will be, of course, remember the conjugation. The conjugation works. Here we did inversion, but the conjugation doesn't matter because top part comes down, down part goes up. That is why I only took care of the inversion. Exactly, exactly. If it says imaginary part positive, it you need to apply conjugation, but in this case, didn't matter. Okay, all right. Well, good questions. I'm glad you are studying hard. Do study harder. Remember, when you come and you take the test next Thursday, you don't invent complex analysis during the test. You should come completely prepared to take the test, all right? Completely. Um, Today, I guess I covered section, let's see. Oh, well, 12.17.2 is linear fractional transformation. I covered it on Wednesday, last Wednesday. The same thing with 17.3. Today I covered sine Z, and sine Z, as I said earlier, your text, unfortunately, is very brief in these type of things, and but my lecture should help you a lot. So today I talked about 17.4, and among the functions discussed in 17.4, I simply concentrated on sine Z. Okay, sine Z is good enough. So you learn sine Z the way I talked about it. We don't need those hyperbolic sine Z or something. Just sine Z will be good enough. It was 17.4, sine function. Okay. All right. If you don't have any other question, then I'll see you on Thursday. Don't forget to go online. I guess you were asked or you were sent a link. Please go to the link and evaluate the course as well. All right. I'll see you on Thursday. Have a good day, everybody. Bye-bye now. Thank you, Matthew. Thank you, Corey. Thank you, Dale. Thank you, Krish.